Hi students, welcome back to the part B of the third video lecture on sampling. So we will solve an example here and we'll give you a couple of exercises for you to solve. Okay, before doing that, let me just add one more point to what we have already been discussing in the first part of this lecture. So let me hope I am in the desktop sharing mode. Things are coming correctly. Okay, so what I would like to consider here is, wait a minute, just adjusting the stand. Okay, so what would like to write is how to express the XR of, for example, this is how to express the Fourier transform of this, which is continuous time, XR of j omega, in terms of x of e power j omega. Okay, so here you could write, for example, XR of j omega is, how can I write that? Let me write here. Okay, there is enough space here. Let me write here. So XR of j omega is obviously equal to x is equal to the reconstruction impulse filter. What we had there is HR of j omega, and this is getting multiplied with x s of j omega, and then xh of s of j omega you could write it in terms of x of e power j omega. So there is just a scaling happening there, and that relation we already know from the previous ones, omega t by omega, right? And so this is nothing but x, okay, x of e power j in place of omega t. This is the relationship between the CTFT of the reconstructed signal and the DTFT of the input. If you start the that module from x of n, that's the relationship. Okay, with that now we are done. We'll for some time with the theory, and let's work out an example now. Let's consider a signal, a simple sinusoidal signal. Assume that your xc of t, okay, hope you remember xc of t, that's in the very beginning of your block diagram, is equal to cos of omega naught times t. Okay, what is the CTFT of this? So first, as a first step, let's find it out. What is the xc of j omega of it? You pause it and you try it yourself if you want. Okay, how do you compute that? Well, the moment you see cosines and sines, you write it in terms of the complex exponentials, which are the eigen vectors of the Fourier transform, right? So you could write it as 1 by 2 e power j omega naught t plus e power minus j omega naught t, correct? And then how do you find out now the Fourier transforms for this? Well, you know, for delta of n, the CTFT is 1. Okay, so if you have 1 here, from that you would get that this is equal to 2 pi times delta of n. Now you use multiplication by e power j omega naught t. Okay, that CTFT is equivalent to what does it do? It shifts in the other side. Okay, sorry, this I should have been written as 2 pi into delta of omega. Okay, one more correction here, this should not be using square brackets, that should be this delta of n. So e power j omega naught t would give me 2 pi into delta of omega minus omega naught. That implies I would get now, you use that now for minus j omega naught also. Xc of j omega is equal to pi times delta of omega minus omega naught plus another one at omega plus omega naught. Okay, this is your xc of j omega. Let's plot that out now. Let's call this as omega. Okay, somewhere here 0. You have one value at minus omega naught, another impulse at plus omega naught. What you have there are impulses, and that magnitude getting multiplied by pi. Okay, this is your magnitude of xc of j omega, or I could say simply xc of j omega, right? Then first case we will consider is we have plotted for xc of j omega. Now what is it that we are going to do now is to plot it for xs of j omega. Let's plot it for, after multiplying this signal in the time domain with an impulse train, what would be the resultant magnitude spectrum. That's what we would like to draw here. What would happen then? This magnitude, okay, whichever is there at omega naught, would still come at omega naught only, but that gets scaled, its magnitude gets scaled by value t here. Okay, similarly assume it's a straight line. Okay, this is pi by t, this is at minus omega naught, this is at omega naught. Okay, and for a purpose that would be clear to you shortly, I would prefer drawing on one side with blue color and on the other side with red color. Okay, now now you consider case of without aliasing. Okay, that's what we would consider now, without aliasing. If you draw this out, next one will, this would be placed at omega s, correct? That would be greater than 2 times omega naught. Okay, this, for example, this roughly here, let me put somewhere here omega s, and this again, a copy of this is placed there. Okay, so this would, let's say this is pi by t on the left hand side of this copy, and on the right hand side pi by t. Okay, this also let me write then pi by t. Okay, or I could even drop writing the magnitude for the rest, right? Let's also plot it for the other side here. Okay, this much distance. Okay, yeah, let's assume somewhere here minus omega s. So left side copy is pi by t magnitude here. I have one more copy on the other side at minus of omega s plus pi by t. Okay, well, so this, by the way, is at omega s minus pi by t. Okay, yeah, this is how this copy would be there. Now if there is no aliasing, what would you do now? This is, what is it that we have drawn? This is the magnitude spectrum. This is the magnitude spectrum of xs of j omega. Okay, This is your omega. I'm skipping plotting x of e power j omega. If you want, you could do that as well. Now let's now draw what is the low pass filter. How does that look like? That low pass filter, let's draw that out now. I don't need to draw it so long anyway, that would be here. Okay, that would come somewhere omega s by 2, so somewhere here it would come, correct? And similarly it would come here, somewhere here. Okay, and so let me draw it this way. What should be the multiplication factor here? That should be t here. Okay, and what is it that I have drawn here? Magnitude of h of j omega, and then you multiply both. That would give you again, of course, exactly. If you want, I will write here for the sake of completion. So your omega, okay, when you are pi by t into, so this coming here, pi by t multiplied with t, having magnitude pi at omega naught. Similarly here at minus omega naught, this again pi by t multiplied with that would give you pi. This is your magnitude of xr of j omega when there is no aliasing. This is with no aliasing case. That's important thing, because in the next subsequently we are now going to look at what happens with aliasing. So that's exactly the same as, of course, your hc of j omega. You simply take inverse continuous time Fourier transform, should give you back the original signal. Okay, hope this is clear. So now let me do the same thing for with aliasing. Okay, without aliasing it's clear. Let's do the whole stuff again. It was a little bit painful, but let's still do that with aliasing. Okay, so let me quickly again draw omega. Let's start again with this xc of j omega. So how does it there? It has values. This is essentially is same here. Okay, again yeah, let me draw this thing in red. Okay, this thing in blue, and this is at omega naught, this is at minus omega naught, and what I have drawn here is magnitude of xc of j omega. Now next what I would like to draw is magnitude of xs of j omega. So what would be happen here? This anyway would be here at omega naught. Okay, and this here, this is pi, this is also pi. You get that with pi by t. Okay, and this you would get with magnitude of pi by t again, right? And this is omega naught will remain same. The next copy omega, so when there is aliasing, what does that mean? Your omega s is less than 2 times omega naught. Okay, so this distance, so somewhere it would come, that could so assume that your omega s is here now. Okay, and if I plot the left hand side, this would bring that a copy here, and another copy would go from here. Yeah, and same thing here. Um, this is, assume that this is your minus omega s. Left hand side copy would come somewhere here, and the right hand side copy would go here. Okay, and what is this, by the way? This is equal to omega s minus omega naught. Okay, so obviously here you could see omega s minus omega naught will be less than omega naught, so that's why this has come on that side. Okay, and by the way, now let's come to the filter part. Okay, let me, yeah, by the way, this is the line I have here, that's the 0. Okay, and this what I have drawn is magnitude of x s of j omega, right? Right, now I need, what I am going to draw now is magnitude of h of j omega. Where will it have the filter? That filter will be at omega s by 2 is the cutoff frequency. So this also you could say from here that omega s by 2 will also be less than omega naught, just from here to here you could say that. So that means the cutoff frequency would come in between omega s minus omega naught and this one. So the cutoff frequency omega c would fall now somewhere here, and similarly somewhere here. Okay, this is your filter, and of course this gets multiplied by t. This is your y-axis, and this value is equal to omega s by 2. Okay, or else I could write it as pi by t also. Okay, this I could do 2 pi, because omega s is 2 pi by t, so this is equal to pi by t minus pi by t. So you multiply them both, see what you are going to get here. That's, this is again omega, this is again omega. You multiply them both and you would end up with 1 will, which is here. Okay, at omega s minus omega naught you had this. Similarly you had one more here. Okay, so this value is at omega s minus omega naught. The same logic, this would be minus of omega s minus omega naught, and this getting after getting multiplied with t, you have here pi, and this is your magnitude of xr of j omega. Can you now tell me what is xr of t here? xr of t is nothing but cos of omega s minus omega naught times t. This is the result with Aliasing. Okay, originally it has to be cos omega naught t, but the moment you are not taking enough samples within, or your t is very large, that's when you are ending up with a different signal due to Aliasing. Hope this is clear to you. Okay, this is the effect of Aliasing, and let me now give you a couple of exercises to work out, which would make this concept a bit more clear. Okay, the first exercise for you is, you take, so far I haven't taken any numbers for it. So let me give it so that you will be able to see it in a less abstract way. Assume that your xc of t equal to cos of 4000 times pi t. Okay, this is the, assume that this is sample, the signal is sample with a time period of t equal to 1 by 6000 seconds. Okay, with that, then you plot, what all can you plot here? Xc of j omega, let's say. Okay, the Fourier transform of it after multiplying it with a impulse train, and then the CTFT of it. Okay, and you get a discrete version of it. So you can also in fact plot x of e power j omega, all they haven't plotted there. From that you again do the inverse of it and then use low pass filtering and everything. Okay, and of course during low pass filtering you get h of j omega, and anyway finally you get xr of j omega. Okay, this is what I want you to do it. Okay, right. So that's the first thing you do, and the second exercise that I would give you is in similar lines, but now you take xc of t is equal to cos of 16,000 times t, 16,000 times pi t. Now this is the input signal. This is again is sampled with the same time period as the previous one, so that is t equal to 1 by 6000 seconds. Now you again plot all those things, then you plot xc of j omega, xs of j omega, x of e power j omega, h of j omega, and the reconstructed signal also you plot it. Okay, yeah, if you want you could plot xr of t also. Then you would notice an interesting thing that in fact xr of j omega would be the same thing, the second one resulting in aliasing. So I want you to compare the results you obtained here with the results that you have obtained in exercise 1, and then you get an explanation on why both of them result in same x of n. Okay, this is the exercise for you. I don't want you to directly use this result of xr of t equal to cos of omega s minus omega naught t for aliasing. Rather, I would like you to do this practice in the similar lines I have drawn here, so that these concepts will become pretty clear to you. You will without any questions, doubts there. So that's what I would like you to work out. So please work out these two problems. Okay, that's all for now with the reconstruction of the given discrete time signal. So we'll stop here. Okay, that's all for now. So let's take another topic in the next video lecture related to sampling. Okay, yeah, hope you understood things. If you have any questions, we will discuss it in our meeting, conference meeting. Okay? Yeah, thanks for watching. You could post your questions in the comment section as well. Okay, see you in the meeting. Yeah, bye.